a very important topic within vector calculus is line integrals. And line integrals serve many quote-unquote real-world applications. And we'll explore a handful of applications at the end of this lecture. This lecture will probably take up 2 videos. And so by the end of the second video, I would presume that we'll discuss some physics applications, right? And we know, if you like to think about it in this way, math is applied logic, and then physics is applied math, and then engineering is applied physics. And so you can see from math, you can go down the chain to physics and engineering and et cetera, and you get a lot of applications. But first, let's just start with learning what these things do and what they are, how they're set up, etc. So there are 2 types of line integrals that we will discuss. The first is a scalar line integral. And the reason it's called this is because we'll be integrating a scalar function. We also have vector line integrals. And this is where we'll have to recall our notions of vector fields from the previous lecture. And this is integrating vector fields. Okay. You remember, you may say like, well, how do you integrate a vector field, right? Well, you could remember we integrated vector valued functions, which was basically integrating vectors, right? And so we can do kind of the same thing here, but now instead of it being like vector valued functions with parameterizations, et cetera, we're just looking at vector fields here. But it's still vectors whose components are functions of variables, right? And so let's start with constructing a formula for the scalar line integral. And first, let's understand what is the scalar line integral going to do. The scalar line integral, so you can look in 2D or 3D space. Imagine we have some smooth curve C in 2D or 3D space. Okay, and for this picture, I'll just draw 2D, but you can, this construction works for 3D as well. You just tack on X's everywhere, right? Or it's not X's, you tack on Z's everywhere. So let's look at some curve in the XY plane, right? This smooth curve C can have a parameterization given by R of T, right? We've learned this for, let's say, T goes between points A and B. And so here you have like R of A, and then R of T describes like the path a particle would take moving along this curve, and then ending at the point R of B. And what the scalar line integral is doing is, we've talked about integrals involving curves before to calculate arc length. But here we're actually looking like the standard notion of an integral as being like volume above some domain and below the function over that domain. But now it's just a curve C in the XY plane. And over this curve, we can see how some scalar function, let's say f of x, y, z. So let's make this 3D, x, y, z. And let's say R of t is parameterized, or the parameterization is given by like x of t, comma, y of t, comma, z of t. Okay. And so you can imagine this curve now just being in 3D space, right? And then you can look at some scalar function over this curve C, right? And it's going to also be a curve. This part of the function over the curve C will also be a one-dimensional curve. And you get almost like a curtain or a sheet here. You can think about this as like a curtain or sheet with an upper bound of f of xy over your curve C. And what the scalar line integral does, we say, we express the scalar line integral as, so I'll write here some notation. We express the scalar line integral as the integral over the curve C of S ds. This is the area of the curtain or sheet that's shown here. So this is what the scalar line integral will be telling us, right? And again, this is different from any integrals we've seen involving just standard curves in this class so far, because now we're actually calculating area of a sheet. We're not using it to get like arc length or something like this. And so now we want to see, how can we construct this, right? Well, we have this parameterization. Like, how can we construct a formula for this integral? That's what we'll be doing here. We have this parameterization here. And so we can subdivide, right? We can partition our t interval here. So let's partition, kind of the same old song and dance when you're defining integrals. Let's partition this interval AB into n subintervals. So we can say, like, of equal width. So let me write here, like, equal width, right? Actually, not even. Don't listen to me. I mean, do listen to me, but not right there. So we have, let's just say like A is T0. No, we do. We want the T intervals to be equal width. Sorry. Don't listen to me telling you not to listen to me. Listen to me. So we'll say A is T0, T1, like up to some indexed Ti, all the way up to Tn, which we'll say is B, right? And so now we have, like, we can look at a partition. We can take the partition of our time domain, right? This is T. The domain for T here is this interval A to B. We can take this partition of the time domain to partition the curve. So we can partition the curve via this partition here, right? What we can do then is say, well, let's call R of T naught, let's call this point P0, and R of T1, let's call this point P1, et cetera, et cetera. And so the general formula here is R of Ti is the point Pi. And what we'll get is, what we'll get is a partition of the curve here, right? This is like P0, P1, P2, all the way up to some Pi minus 1, Pi, all the way up to Pn. And so now let's say these are the intervals that may not have equal length. We'll call the length. So we'll call this curve C1, the next curve C2. And so the curve, the subcurve with endpoints Pi minus 1 and Pi, we will call Ci. Okay. And so curve CI has endpoints PI minus 1 and PI, right? So then the length of the curve CI, what we'll call it is delta SI. We usually use the variable S to indicate arc length. And so we'll describe the length of these subcurves here, I was using blue, as like, so this has length delta S1, and the ith one has sub length, or length delta SI. Okay, and now, what do we want to do, right? We want to find the area of this sheet over here, right? And if we're partitioning this curve, we think about our approximation method that we've been using all semester when defining integrals, right? You take the area over a subinterval, an approximate area based on a sample point, and then you add up all those areas and then take the limit, right? This is no different, so we're going to do the same thing. And so that means we need a sample point in every interval. So in every interval, or every subinterval, we're going to pick sample points pi star. And so we have these sample points pi star that belong to the interval pi minus 1, comma, pi, right? And so now what we need to do is approximate the area of one of these subrectangles. So what we're going to have here, as you can imagine, say this is the curve CI, and then we have the function over this curve. So we have f, right? Well, now we pick some point in here, pi star, and we can use this pi star to approximate the area of this almost rectangular shape, right? It's not quite rectangular, but we're going to approximate it via a rectangle. And the rectangle is going to have base length, delta SI, and height is going to be by taking the sample point and evaluating the function at this sample point. And so we'll say this is f of pi star, right? That's the height here, is the height is the function, right? Or it's the function evaluated at that point. And so we get an approximate area, so like the ith area, we'll say, right, which is going to be the area of the sub sheet or curtain over CI. This is going to be approximately, well, so the area, let me say the area of the ith piece here, we can take f of pi, right, because this is base times height. So f of pi star times the height, which is, or the width, which is delta SI. And so that means the area is approximately the sum as I goes from 1 to n of f of pi star delta SI. Okay, and so then A, so let's give a definition. The scalar line integral of f along smooth curve C is given by, and we write here this notation of f ds, right? And this works for 2 or 3-dimensional case. That's why I've been leaving how many variables we're talking about out of it, because it's the same construction either way, right? And this is the limit as n tends to infinity of this approximate area, right? Because as we take these sums to be greater and greater and greater, the delta SIs become infinitesimally small, and then this becomes no longer an approximation. And this is the limit. I goes from 1 to n of f of pi star delta SI. And Once again, this is good for constructing the definition, but it's not good for using it to actually solve problems, right? You can do it. It would be horrible, but you can do it. Now what we want to do is construct, hopefully, an equivalent definition so that this is much easier to compute. And this is what we'll be doing now. So now that we've defined what a scalar line integral is, and it's giving us the area of this sheet that's kind of draped over the curve C here, where the top of this curtain is the function above C, right? So let's now see if we can define an equivalent formula for the scalar line integral that makes this much easier to compute. So notice we are under the assumption that C is a smooth curve. And so if we use that assumption, C smooth tells us, so C smooth implies that R prime of t of our parameterization, which is, if you'll remember, x prime of t, y prime of t, z prime of t, this is continuous on C, right? And so we know the length, as we mentioned before, of CI is equal to delta SI. Well, now let's think back to our knowledge of vector valued functions. We had a formula for calculating arc length of a vector valued function, right? And so now we want the arc length. We want this delta SI of a very small one of these subintervals here. Well, if you remember, arc length, calculating arc length of a vector valued function, right, is given by the integral from your lower bound to your upper bound, which for us in this, on the curve CI, the endpoints are TI minus 1 and TI, right, of the magnitude of R prime of T dt. So if we take TI to be like sufficiently close to TI minus 1, this curve CI is almost linear, right? So if TI minus 1 is very, very close to TI, like sufficiently close, then CI is almost linear, right? Like if these points were like very close together, then your curve, this subcurve CI, is almost linear. And what that means is that we get an approximation for this integral, right? If this integral is very, very small, well, this is almost just the integral of some test point Ti star. So here Ti star belongs to Ti minus 1 Ti. This is approximately the magnitude of some test point times the change in width here. So like delta Ti is Ti minus 1, right? If this is linear, we can make this approximation. So what this means then is when we write the sum here, so I goes from 1 to n of f of r of t delta si, right? This is before taking the limit. This is our formula. Remember, before taking the limit, this was our approximation of area, right? But now I'm looking at pi. Remember, pi star is going to be equal to r prime of Ti star, because this is how we defined the points Pi and Pi star in the first place, right? You can see here. This is how we define those points. So expressing this using, so sorry, this is Ti star here. Ti star. Using this, we can write sum I goes from 1 to n f r of Ti times r prime Ti star delta ti, using what we just made this approximation, that delta si is approximately this value here, right? Because again, we're assuming that this ti minus, we're assuming that ti and ti minus 1 are sufficiently close. And so what this means is taking limits gives us the following theorem. If we take limits, then we get that the scalar line integral, which was f ds, right? Because on the left, when we take the limit, we'll get the previous definition that we had right here, right? But now we're writing pi star is this. And then on the right-hand side, what we'll get is the following. This is the integral from a to b. So take limits. Again, take limits as n tends to infinity. And here's what we get, right? Here's what you get from this statement. We get this is the integral from a to b of f of r of t times the magnitude of r prime of t dt, right? And so this is a much, much, much nicer way of computing a scalar line integral using this formula. And so this is where C is parameterized by R of t for t between A and B, right? Just so we can make more sense of this side of the equation. And so to compute a scalar line integral, you need to plug your parameterization of your curve into the function, find the magnitude of the derivative, whatever this expression turns out to be, you integrate this from A to B, and you get your line integral. So let's do an example here. Let's evaluate the scalar line integral of the function x squared plus y squared plus z ds, where c is parameterized via r of t equals cosine of t, sine of t, t, where t ranges between 0 and 2 pi. And so if you're interested, maybe you'll remember from our discussion of vector valued functions, this is a helix from, it's like one rotation of a helix, right? Because in 2 dimensions, we're doing cosine t, sine t, which is a circle. And then t says that as t goes on, you lift this circle. And the result is a helix, or like an expanded slinky, right? And so just so the idea of the curve that we are taking the scalar line integral over. All right, so let's evaluate this, right? Well, we need 2 things. Let's remember the formula of f ds is equal to integral from a to b f of r of t times magnitude r prime of t dt, right? So we need f of r of t, and so here f of x, y, z is this function right here, right? Well, no ds, right? No Nintendo DS. All we have is, for the function, is x squared plus y squared plus z. And so f of r of t. And so when I'm solving these problems, I like to figure out what like each piece is and then plug it all back in, right? You certainly don't have to do that if you don't want to. But that's what I like to do. So let's find f of r of t first. Well, we know the x component is cosine t. So this is going to be cosine t quantity squared plus the y component is sine. And so we have plus sine t quantity squared, and then plus z, which is t, right? And so you'll see this becomes cosine squared plus sine squared plus t, which is 1 plus t, right? So f of r of t is 1 plus t. Now let's find the magnitude of r prime of t. So the magnitude Well, first we need to find r prime of t, right? The x component was cosine. The derivative of cosine is negative sine. The y component was sine with derivative cosine. The derivative of t is 1. So here's r prime of t. Now let's calculate the magnitude. R prime of t. This is root. Then you take each component, square it, and then you sum them up. So negative sine t squared plus cosine t squared plus 1 squared. And you see the sine t plus cosine t will be 1. And so we'll get 1 plus 1, which is root 2. And this is what was the magnitude of r prime of t. The next things we need are the bounds, a and b. Well, it was given in the problem, right? A and b are the bounds for t. So a is 0, b is 2 pi. Now we have every piece. Let's set the integral up. So the integral of CF ds is equal to, well, let me be more clear here. X squared plus y squared plus z ds is equal to the integral from 0 to 2 pi of root 2 times 1 plus t dt. Well, this is root 2 t plus 1/2 t squared from 2 pi to 0. You plug in 2 pi, you're going to get root 2. So, well, if you plug in the 2 pi for t, you're going to get 2 root 2 pi in the first term. And then in the second term, you'll get 2 pi squared, which is 4 pi squared over 2. So plus 2, and then there's a root 2 out front, root 2 pi squared. You plug in 0, you get 0. And so here is the line integral, the scalar line integral for this given function over the given curve, right? And so here's an example of how we can actually compute a scalar line integral. And so this gives us a nice definition, a nice working definition, and a good example of scalar line integrals. What I'll break here for this video. In the next video, we will discuss vector line integrals, and I'll do an analogous construction. I'll construct the vector line integral. I'll construct a working definition. I'll go over a nice example. And then at the end of that video, quickly, what I'll do is list some applications of line integrals. How can we use these in physical settings?